with the front slide. Alright, so this is just for the video. I'll just say that this is using Camtasia, and I hope this comes out okay. It's done live in class, and fingers crossed that it's all working well. So it's a bit of an experiment. More about voltage dividers. I've said here, why does it equal 0? And the next page we've got this circuit which has got two series parallel circuits, and I'll call them circuits, not branches, because there are just two branches, 1 and 2, but each branch is in series. So branch number 1 has two 1K resistors in series, branch number 2 has two 1K resistors in series. Probably a little bit confusing after some of the material that we've done, because we haven't seen a circuit so far with a voltage source in the center like this one is set up. We could redraw that, and we could position the 5 volts over to the left hand side, and then perhaps it would look more normal, would it? Aaron? Does that make sense? If I'll just go to the board and I'll do that. Look, I might just work here. So, supply, and let's just group them together. So this represents, they haven't got numbers, but that's the 2 times 1K on one side, and this represents the 2K, 2 times 1K on the other side. So there's 4 resistors there. This is 2 resistors, this is 2 resistors. There's our voltage source. So the current comes up there, some current goes down there. This is a node, the current splits and goes down there as well. But look where the voltage meter is sitting. The voltage meter is sitting in between the two 1K resistors in each branch, and it's registering 0 volts. That's because the voltage developed across that bottom 1K resistor is going to be the same on each side. And if we just break that down and call this R1 and R2, R1, R2, the voltage at the junction there, this is rail, plus 5 volts. How's that cool? The voltage at this point, here's our voltmeter, the voltage at this point is going to be R2 divided by R1 plus R2 times V supply. And you've seen that equation before. Not familiar with it? Nobody's got any notes open and writing stuff down. Yes, there is. One person is. How about you open your book and you start taking some of these notes, because otherwise I'm going to work pretty fast to get through this PowerPoint, and I'm going to be rubbing stuff off the board. I can't write on the PowerPoint using the Mac. That was one thing where I do miss my Windows computer. It's a tiny thing, but I used to be able to write on PowerPoints, and I can't write on PowerPoints easily in this without another bit of software. I can annotate each slide though when I go back through and I do the editing. If I'm not lazy and I wanted to do the editing in Camtasia afterwards, then I can edit the slide. But you know, when you're teaching this live, it's nice if you can sometimes draw on slides, and that's one little thing I missed between PowerPoint and Keynote. Anyway, neither here nor there. R2 divided by R1 plus R2 times Vs. So we're going to get, because we've got 1K here and we've got 1K here, the voltage at that point is going to be plus 2.5 volts. You can do it yourself. 2.5 volts. If I've got 2.5 volts on the left-hand side of the circuit, between there and ground is 2.5 volts, and between there and ground is 2.5 volts, 2.5, 2.5, this meter is measuring the potential difference between there and there. If it's the same voltage, the meter has to measure 0 volts. Can you see that? Alex, does that make sense? Good. All right, so the next slide does actually explain that. What's WR2? With respect to, very good. You'll see me use this a lot from this point onwards. With respect to ground is plus 2.5 volts, like I just said on the board. And number two, so point number one, point number two, with respect to ground, both 2.5 volts. So of course, there's no difference in voltage between them. And the voltage meter is measuring a voltage difference across 2 points. That's why it's measuring 0 volts. Mahmoud, you happy with that?
No, sir.
I didn't think you were. You had that look of, I don't understand on your face. Okay, ask me a question and help me explain it better.
I didn't get from the first one, sir.
You didn't get from the first one?
Yeah.
All right, this is a voltage divider situation where you can have numerous resistors in a chain like this, and then between this point and wherever you tap off a voltage, you can get different voltages out of a circuit. You could use Ohm's law on this. Can anybody tell me how you'd use Ohm's law to get the voltage across R2? Omar?
V over.
Wait, so what was the question?
How would you use Ohm's law to get the voltage across R2?
V over I.
V over I. How do we work out the current?
Yeah,
I is the first thing we have to get. I equals V on R. It'll be V on RT. It'll be 5 volts divided by 2K. Does that make sense? You've got 2K ohms, 5 volts, total current. So far so good? Right, so once you work out that current, if you multiply that current then times R2, because V equals IR, so that current that's flowing down through that resistor multiplied by that resistor gives you the voltage across it, and that's going to be 2.5 volts.
So we take the total current to V over 2K multiplied by total current.
Multiplied, once you get the total current, it's a Kirchhoff current rule. The
Yeah.
current in a series circuit is the same in each resistor.
Yeah.
Therefore, the current flowing through R1 is the same as R2,
Yeah.
so 5 divided by 2K. All right, get your calculator. You're sitting there looking at it, no calculator at the hand. You know, get it out, have a go at it. Then get that current, multiply it by 1K, and you'll find that you get 2.5 volts. 2.5 milliamps times 1K, 2.5 volts.
Zeros 0.006.
And this is a voltage divider rule.
So this equation here,
Yeah.
that's a V5.
VS.
VS.
V supply. VS. That's 5 volts. All good?
Yeah.
So please make sure you take some notes, because I can see where I'm going here. I'm going to fill that board up pretty quickly. I can get rid of yesterday's material, that SN, ZN. We don't want to know about tin zinc. That was for soldering class yesterday. But I'll try and leave as much on the board as I can. But you know already, I apologise in advance. When I'm working quickly, my board work gets a bit messy. Potential difference, point 1 and point 2 on that circuit are identical voltages. There's no difference in potential. The voltmeter will indicate 0. Questions about that? So we're talking about, just going back there one slide, we're talking between point 1 and point 2, the voltage will be 0. Leon, you happy with that?
Yep.
Simon? All right. New slide, new game. Not really. All I've done is just expand it. Same circuit, from point 1 to ground is the bottom meter, 2.5 volts. From point 2 to ground, 2.5 volts. Again, illustrating that just because you go between one point and another doesn't mean there's no voltage at those points. It means between those 2 points there's no voltage. But from each point to ground, there is voltage. The fact is, it's just the same voltage. If I had though, and I think I'm going to develop this on the next slide perhaps, if I had 2.6 volts there, say I had a slightly bigger resistor there, and we had 2.6 volts there and 2.5 volts there with respect to ground, what would I measure between there and there?
2.4.
It would be 0.1, 0.0.
I've got 2.4, and I've got 0.1. Who thinks 0.1?
Nothing.
I've got a couple of hands up. Who thinks 2.4? Who doesn't think? I don't want to think. I want to go home and have a cup of coffee. The answer is 0.1. It'll be the difference. If I've got 2.5 there and 2.6 there, the difference between 2.5 and 2.6 is 1 minus the other. 2.6 minus 2.5 is 0.1. Leon, try and smile and look happy. You'll give me more confidence. If you want me to sort of say it again in different words, just holler out. Whatever you do, I don't know what slide we're on. Oh, yes, I do. It says slide 5. I'm on slide 5. Don't wait till we get to slide 15 and then say, can you just go back and start over from slide 5? Ain't gonna happen. Each leg is a voltage divider. I explained that before. Voltage divider in each leg, voltage divider, and you know, voltage divider doesn't have to be 2 resistors, it could be several resistors, and we can tap off and have different voltages. You know, when you turn on your little radio set and you're listening to digital audio broadcast, inside that radio there's going to be multiple voltage dividers to supply different parts of the circuit. That's why we have voltage dividers in electrical and electronics. So each leg on the left and on the right is a voltage divider in its own right. What if we change the values? We had 1K, 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 1K. Now that sort of made sense, so we had the same current going down through each leg. But what if now I keep the 1K resistors on the left and on the right hand side I put 2 25K resistors? Get your calculators out. Tell me what the voltage will be between point 2 and ground.
It wouldn't remain just half the voltage, would it?
It wouldn't just be half the voltage. We got half the voltage before. When we had 1K and 1K, we got a half the voltage. If we got 25K and 25K, do we still get half the voltage?
Yeah, because they're both the same, it's just half of the...
They're both the same. And if you work out the current going down through that, we said you've got 5 volts divided by R1 plus R2. So that would be 5 divided by 50,000 ohms equals 1 milliamp. And 1 milliamp times 25,000 ohms, what did you get for it, Leon? Peter Scanlon, what did you get for it?
Oh, I haven't done it.
Haven't done it yet.
So,
Aidan, have you done it?
here the equation says that we would divide R2.
R2 divided by R1 plus R2 times Vs.
So in here you divided the 5. 5 is the which
You
is the
can do
supply
it
voltage.
using Ohm's law, or you can do it using
So I got
ratios.
2.5.
You got 2.5 volts, and that's the answer. That's
So
the
both
answer.
These are same.
Exactly the same. But the current's different, because when we had 25K and 25K, how much current do you get? 5 volts divided by 50K.
0.1.
You get 1 milliamp. But when we had 2K, that's a lot more, isn't it? That's going to be 5 divided by 2, 0, 0, 0, equals 2.5 milliamps. Alright, so we can change the voltage divider resistors from one side of the circuit to the other, but if the ratio stays the same, we're going to get the same voltage. So I've shown the, with the heading calculations anybody on this slide, and I've said R2 divided by R1 plus R2 times VS. That's that equation I've got in the box on the board.
And this equation is to find what?
The voltage from a voltage divider.
Voltage.
We did this some weeks before. You should have done this with the other teacher when I was off sick. The current, we can work out the current, and that's what I did on the left-hand side, simply using Ohm's law. I total equals VS, V supply, V total if you like, divided by R total, RT. And then you multiply IT times R2. I did that a few slides ago. Or when R1 is equal to R2, as, who said that? Matt said that just a minute ago. If they're the simple same resistors, no, I think Erin said it. Same resistor values, we just halve it. So if you've got identical value resistors on the top and bottom, whatever the supply voltage is, the output will be half. That's a really easy situation, that. So far so good? Simon?
Can you repeat the first point?
The first point here, which is R2 divided by R1 plus R2, in the box here on the board. It's a ratio method for working out the voltage from a voltage divider. And the bottom resistance divided by the sum of the two times the supply voltage. And it'll give you exactly the same answer as if you use Ohm's law and you work out the current going down through the network and then multiply that current by the bottom resistor. Because it is the voltage across the bottom resistor is what we're measuring. Look at the ground symbol here, ground symbol here. I'm measuring the voltage across R2. That's the output from my voltage divider. Don't confuse it. And if you've got, like, say you had different value resistors, like 3.3K there and 1K there, don't use Ohm's law and work out the voltage across the 3.3K and give that as an answer. That's not going to work out too well for you. Better to... I think even on your equation sheet that I printed off for you, I wrote down the voltage divider thing. Can somebody check it and tell me? I'm sure I put that on there. Voltage divider. Can you see it?
Mm-hmm.
It's there?
Yeah, it's kind of
I'd be certain it's on the sheet somewhere. Because you'll use that equation from now to eternity. My other class currently doing amplifiers at the moment, we use that R2 on R1 plus R2 times VS every quarter hour. We're using it in class to work out bias voltages. Right, moving along. So, like I said, 2.5 volts in each branch still, 0.1, 0.2. The only difference is with network number 2, it's got less current because it's got bigger resistors. But the voltage is still the same. So therefore the voltage between 0.1 and 0.2, if I get my meter and I put it between here and here, even though I've got different value resistors between here and here, I'm still going to get 0 volts because it's potential difference, the difference between this point to this point. 2.5 minus 2.5 is 0. All right. Moving right along. A new slide. A new game. Let's explain this a bit. Network number 1 on the left is supplied by an 11 volt source. We've got R2 at the top is 2000 ohms. RX, I've called it, on the bottom is 200 ohms. So that entire network on the left is 2,200 ohms or 2.2K. The network on the right, number 2, has 10K resistor at the top, 1K resistor on the bottom. Total resistance, 11K. It's supplied by 11 volts. This blue rail on the top here is, I told you right back in week 1 that I used Circuit Maker, and I showed you some things in Circuit Maker, iCircuit on my Mac, iCircuit. And when we want to find in iCircuit, which is that circuit simulation software, just like what's it called, electronics workbench that we use on the computers here, I can highlight a wire and it'll tell me the current going through the wire and the voltage between that wire and ground. So it's telling me there's 1 milliamp flowing in that wire and there's 11 volts from that point to that point. Get your calculator and work it out. 11 volts divided by 11k. How much current do you get?
Million.
1 milliamp. That's exactly correct. The circuit simulator, when I did this on my computer, told me I had 1 milliamp. Which are 11k, 11 volts, 11 divided by 11,000, 1 milliamp in that branch there. What about the current in this branch here though? This is 2.2k. Can somebody work out the current in that branch for me, please? That'll be 11 volts supplying this branch, 11 volts divided by 2.2k. I'll even do it myself just so you can't tell me porky pies. 11 divided by 2200. I've got my answer. Aidan? 5 milliamps. Omar, are you going to wake up and stay with us, or are you going to catch Zeds?
No.
You don't catch Zeds on my time. Because I want to catch Zeds too, and I can't. I've got to stand up here and perform. Yeah, I know. It's the room's it's comfortable sitting there, and it's really easy to go to sleep, isn't it? But try and stay awake, because if you sleep through this, it's not going to help. 5 milliamps coming down through network number 1, branch 1. 1 milliamp coming down through branch number 2. How much current total have we got there?
6 milliamps.
We must have 6 milliamps. 6 milliamps total. I've even showed it there. I've used the circuit simulator. I've highlighted that wire. It told me I've got 11 volts to ground and I've got 6 milliamps flowing through that wire. We've just run the maths. We found out we've got 6 milliamps flowing down through 2.2k and 6 milliamps current in branch 1. Sorry, 5 milliamps running down through there. The total current was 6 milliamps. 6 milliamps minus the 5 milliamps leaves us with our 1 milliamp, which is flowing over there. So straight away you can see that Kirchhoff's current rule holds true. The sum of the branch currents adds up to the current coming into the node. All right, and I've got some wording on the right-hand side of the slide there to back up what I just said. The branch 1, 5 milliamps, branch 2, 1 milliamp, therefore total current, 6 milliamps. Just add the two branch currents together. Nothing new about that, but just looks a little bit more confusing because it's got more stuff, if I can say that, on the circuit. All right, so we've got two current paths. I1, 11 divided by 2200, 5 milliamps. V1, therefore, we can multiply that 5 milliamps times the 200 ohms. That's our Ohm's law thing that we did on the board 10 minutes ago. And we get 1 volt. 1 volt is between 0.1 and ground. Right-hand side of the circuit, though, I2. 11 divided by 11k, we just saw it, 1 milliamp. We get that 1 milliamp. We multiply it by the bottom resistor to get the voltage across the bottom resistor of 1 volt. So again, I've got these weird values of resistors, 4 different resistors, but between 0.1 and 0.2, I've got no volts because I've got exactly 1 volt on the left and exactly 1 volt on the right. Therefore, the potential difference between left and right is zip, 0, exactly. It's what we call balanced. See this new word we've introduced down here, isn't that lovely? It's a balanced situation. There is no voltage difference. This circuit we're going to learn is called a bridge. It's an electric bridge circuit using 4 resistors, and at the moment we say that the bridge is in balance. There is no difference between the voltage from 1 to 2. The difference can be 0, negative, or positive. You think if we've got a moving coil meter, hey, look at this, I've got a big one over here. I'll try and put this in camera. I don't know, I'll put this here first of all, and then I'll put it in cam. This thing is balanced in the middle, 0. It can deflect to the right and be a positive voltage. It can deflect to the left and be a negative voltage. 0, negative, or positive. Let's put that in the camera. 0, positive, negative. Depending on the difference between 0.1 and 0.2. Circuit changed just a little tiny bit. Rx now is what we would call an unknown resistor. Let's just read what it says on the right hand side of my slide. I made these PowerPoints about 3 or 4 years ago. Took me quite a while to make these. I drew all the pictures by hand, the meters and stuff. The resistors RA or RB or both can be variable resistance. The resistors, the other resistors are fixed. They are adjusted until a null is achieved. A null means a 0. They are then read and their values are used to determine the unknown resistance. So Rx is an unknown resistance in practice, and his value, or her value I guess, can be found after balancing the circuit to have 0 volts difference between points 1 and 2. We saw on the previous slide the word balance. When the bridge is in balance, we get that 0 voltage between 1 and 2. And then we can use some maths to work out the value of Rx. And Rx is equal to Ra divided by Rb times R. Can you see Ra is 10K and Rb is 1K and R is 2K. So then Rx, which is the unknown resistor, we get a resistor we pick up off the bench and we go, oh geez, I can't read the colours on this, they've all been burned off or something, you know, and I've got this Butte bridge and I put this resistor into it, then I can measure the voltage, or I can adjust the other resistors on the left hand or the right hand side till I get a null of 0, and then I can measure each resistance with another multimeter, and then I can work out the value of this mathematically using that equation down on the bottom left hand side there. So solving Rx here, if I've got Rb equals 100 and I've got Ra equals 10 and I've got R equals 25, Rx must work out to be 250 ohms. All right, now I'm running a little bit short on time for this video. It's been going now for almost half an hour, so I'm going to try and zip through and just finish this off a little bit faster, because don't worry too much about the maths. I'll be giving you these equations. Activity 1, find Rx and then find I1 and I2 and I total. All right, so we're told that R is 15K. We're told that Ra is 10K. We've adjusted Rb, which is a variable resistor. You're still catching Zeds, Omar. Geez, you must have had a long night. Oh, she was a lucky girl. We've adjusted Rb till we get 0 volts across point 1 and point 2. And we then measured Rb with a multimeter. We took it out of circuit, we measured it, we found out it was 22K. So we've got 15K, 10K, 22K. Find the value of Rx. And this is a Wheatstone Bridge, people. We're going to see this name up here in the next few slides, a Wheatstone Bridge, can be used to find an unknown resistor. Solution. I've got it done for us. Rx is RB on RA times R. There's the maths, 33k. I1, we knew we had 50 volts. We've got the resistances. We add them together, divide that into 50 volts to get 1.04 milliamps. I2, same deal, 1.56 milliamps. It's all Ohm's law, people. There's nothing new about it. It's simply Ohm's law and balancing the bridge. I total, you know that. You've got two branch currents. What's the total current? Add the two branches together, 2.6 milliamps. Sensitivity. When you use a commercial Wheatstone bridge, and I'll show you one later on, it's an instrument which usually has a fairly high voltage inside. Unlike a normal digital multimeter which just runs on 9 volts or something, 9 volt battery, these things often run on about 100 volts. And they use a much higher voltage so they can have more sensitivity for low value resistors. Now, where do we use something that we need so much sensitivity with a low value resistor? Well, people working on telecommunications cabling, and they've got a cable which is perhaps 0.5 kilometre long, and they want the exact resistance of the cable. But it's a very low resistance value, and you can't just use an ordinary multimeter to measure it, so they have to use a Wheatstone bridge to get an accurate reading of the resistance. And in fact, if they know the resistance of that copper wire per 100 metres from a table, and then they measure a particular resistance with the Wheatstone bridge, they can work out exactly how far down the cable perhaps a short circuit is. It's a really handy thing that telecom workers use all the time. So more voltage supplied to our Wheatstone bridge will increase the change across the voltmeter due to small resistance changes. And I've already run some maths on that, and I've come up with these wonderfully weird values such as 33003 divided by 48003 to give 68.7519 volts. And if we minus one voltage from the other, we get 1.9 millivolts for 3 ohms. So, you know, if you had a much lower voltage there, you wouldn't be able to get the precision, you wouldn't get the accuracy. Working with larger voltages allows us to get down and work with lower value resistances. Sometimes we see the Wheatstone bridge drawn differently. Oh, look at this, golly gosh, is it all the same circuit? Yes, it is indeed the same circuit. Down on the bottom left-hand side, that's my drawing. I've redrawn my circuit just a tad differently. It's still got a branch on the left and a branch on the right, but now I've moved the voltage supply across to the far right-hand side. And the voltmeter, sometimes called a galvanometer in a really sensitive unit, is still going from the junction between R1 and R4 to the junction between R2 and R3. So it's exactly the same circuit as what we've been looking at. Above that, there's our galvanometer, VG, and it's going between points D and B, but just R1, R2 are drawn on an angle compared to where I had them drawn before vertically. R3, R4, or RX are also on an angle, supply coming in from the left-hand side. Very standard way of drawing a Wheatstone bridge, that circuit. And the circuit on the right-hand side, same deal. It's drawn in that diamond shape with the voltage between the two outside corners and VN supplied on the left-hand side. They're all the same circuit. There's no difference between them.
So these resistors, are they in parallel or series?
Which ones?
These four? The R1,
R1 and R2, if we look at this top circuit, good question, if we look at this top circuit, it's just reviewing what we've done. He's in series with him. Positive comes up here, plus 5 volts, ground, or 0 volts. R1 and R2 are in series. R3 and RX are in series. But these two are in parallel with these two. That was what I said back in the very first slide that we saw. So we've got series parallel in a Wheatstone bridge.
How did you know that R1 and R2 are series?
Because the current comes along here. Little electrons crawl up here, bubble, 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 and they bubble all the way down through here and down through here. So if the electron flow can come down through, well, the conventional current flow can come down through here, they must be in series. And if it comes down through here, they must be in series. But because that network and that network, or those two branches, are right next to each other sharing the same voltage, they are in parallel. So the resistance between, or the addition, the sum of the resistance R3 and RX is in parallel with the sum of those two resistances over there. Like I said last week, this stuff comes pretty thick and pretty fast. Wheatstone Bridge, there's that lovely name I've been mentioning, for measuring an unknown resistance using a null method. When voltages in each leg balance to zero, the unknown resistor can be determined. And there's our Rx, the unknown resistor. So we adjust the value of R2 till the galvanometer indicates zero, and that means that between D and C we've got the same voltage as between B and C. And then we can measure the value of R2 outside of the circuit, and we can run the maths on it as I showed before, and we can work out the value of Rx. That is how a Wheatstone bridge works. Where's Wally? I don't know, Wally's not in that picture, but it's pretty technicolor, isn't it? I love it. There's our Wheatstone bridges. The one on the top left-hand side is the one which I have in this classroom, and the one on the right-hand side is another commercial one. They're both commercial, of course. These things are quite expensive. The one on the top left, we bought 5 of these many years ago. They're made in Japan. The resistors inside them would be extremely low tolerance resistors.
What do they exactly do, sir?
The Wheatstone bridge, like I just said, we put an unknown resistor across these two terminals, Rx, and then we adjust these till we get a 0 reading on the meter, and then whatever the reading is on these individual knobs, and then the multiplier multiplying that reading, whatever that reading is, that's what the resistor is equal to, because the bridge is equal, the bridge is balanced. This is our balancing meter, positive, 0, negative. We're going for a null on that meter with the Wheatstone bridge. So inside the Wheatstone bridge, there'll be several batteries and maybe even a thing called an inverter to step the voltage up in the batteries to about 100 volts or maybe even more. And we put the unknown resistor there. And low value resistors especially, like a multimeter, I've shown you this before. If you get the leads on your digital multimeter and you put them together, it's going to say about 0.7 of an ohm. So how the heck are you going to measure something which is only 0.03 ohms, 30 milliohms? You can't measure it using a normal multimeter. But using a Wheatstone bridge, you can measure 30 milliohms. No problems at all. So for reading very low value resistances, this is an ideal instrument to use. And that is the end. And this has been Greg Moore from TAFE New South Wales. Thanks for watching. Make sure you go back over this video again. I'll try and fix the links in my website and so you can download the PowerPoint, but at the moment the links are still broken because Dropbox has decided to stop all rendering to external HTML sites.